Every day, students in Hwa Chong institution consume an estimated 1.12 tons of food. This raises an issue of sustainability. Our school depends entirely on external food sources, while simultaneously generating food waste. Urban farming, the practice of growing crops in non-agricultural areas, could go a long way in improving sustainability. But implementing it in Hwa Chong is no simple task, as potential farming areas face high temperatures, uneven sunlight, and unpredictable airflow, all of which could seriously hinder plant growth.
Most crops have specific environmental needs to maximize plant growth. Plants rely on light, water, carbon dioxide, and nutrients for photosynthesis and growth. Too much heat or too little light can reduce growth rates or damage plants entirely.
Existing approaches are dissatisfactory. Indoor farming is capable of producing high yields in a space-efficient way, but it's far from ideal in school because artificial lighting and cooling systems lead to significant energy waste. Simple gardening avoids the energy cost, but plants would struggle to survive Singapore's heat, and it is also highly maintenance intensive.
Therefore, any viable solution needs to directly address these constraints. Minimizing waste is essential.
Our proposed solution is an integrated, sustainability-focused farming system to maximize yield while minimizing waste. The location we've chosen is currently an unutilized plot of land outside Block D.
The first component of our system is a gravity drip irrigation setup. Manual watering simply isn't reliable enough, so instead, we've designed a system that waters plants automatically without any pumps. Water stored in a tank positioned at a greater height carries gravitational potential energy. As water flows downward through tubes, potential energy converts into kinetic energy. The pressure driving the flow is described by the formula P equals rho GH. As such, the higher the tank, the greater the pressure and the more consistent the flow. Precisely sized holes allow us to control the flow rate to match exactly what each plant needs. This prevents overwatering, which can cause root rot, and underwatering, which leads to wilting. And because no pumps are required, the entire system is energy efficient.
The second component is a shade net cover, which reduces ambient temperature by 2 to 5 degrees Celsius, preventing overheating in Singapore's climate. Positioning it in open space also allows natural cooling through convection. Plants cool through transpiration. When stomata open, water vapor diffuses out the leaf, requiring latent heat of vaporization of 2,260 kilojoules per gram, cooling the surface through endothermic process. In Singapore's humidity, transpiration is less effective because of vapor pressure gradient, the difference in water vapor concentration between leaf interior and outside air. With very saturated air and direct sunlight, heat dispersion is limited. The shade net blocks 40 to 70% of incoming solar radiation. It keeps leaf temperature safely within 25 to 35 degrees, where the stomata remain open. CO2 diffuses in continuously, and the full photosynthetic equation can proceed. Simultaneously, water vapor exits, keeping the plant cool.
The third component is a composting system, which we intend to install within Hwa Chong's canteens. Composting breaks down food waste into farming soil without needing external power, taking 2 to 8 days. The science behind composting is aerobic respiration. Bacteria and fungi consume organic molecules and oxygen, producing carbon dioxide, water, heat, and simpler organic compounds. For example, composting of starch begins with hydrolysis, where microbes use water and enzymes to break starch down to glucose. It is then oxidized to produce carbon dioxide, water, and heat, raising the temperature of the compost to around 60 degrees Celsius. The organic matter that isn't fully oxidized recombines into complex carbon-rich polymers containing carboxyl and phenolic groups, forming chemically stable and fertile material we can reuse in our farm. Critically, this means food waste no longer needs to be incinerated, a process that consumes enormous amounts of energy due to the water content in organic matter.
Now, let us walk through the 3 crops we have selected as best suited to our system and our goals. First, kangkong is capable of asexual reproduction. It can grow from cuttings without seeds. This makes cultivation easier, and it's also a great educational demonstration of vegetative propagation. Second, cherry tomatoes. They flower before bearing fruit, allowing students to observe firsthand pollination and fruit formation. Their combined growth means multiple plants can also fit within limited space, and they are quite pest resistant. Finally, sweet basil germinates quickly and forms leaves fast, allowing it to begin photosynthesizing earlier, being ready to harvest within just 4 to 6 weeks. Its leaves also feature waxy cuticles that reduce existing water loss, while still allowing photosynthesis or natural adaptation to prevent desiccation in tropical environments.
These systems can ideally create a self-sustaining farm, which will contribute to the food supply of our school through concepts like the vapor pressure gradient and exothermic reactions. This lets us strike a balance and get the best of both worlds.